Okay, so the second speaker this morning, Zsolt Patakfalvi, like that stable variety.
So thank you very much to the organizers for inviting me to speak here, for the audience, for staying for the last plenary talk of the week. And then as the last plenary talk, let me also thank the organizers for the whole organization of the first week. So let me start with a very short personal story. When I was a small little boy, I had a cup, and the cup was wider in the bottom than on the top. And so I called it the stable cup. And I don't know if the organizers knew anything about this story, but anyways, very happy to talk about stable varieties, also called KSB or KSBA stable varieties, after Kolar, Sheffer, Baron, and Alexeyev. He let me just call them stable varieties. For many reasons, historically they were just called that, and in all my articles are just that. But also that emphasizes the fact that in dimension one, they just specialize to stable curves. So their moduli space, I'd like to denote in this talk by M and V bar, where N is the dimension, V is the volume, and so curly M or Gothic M is the stack, Roman M is the coarse moduli space, and so there's an open part of this moduli space which is the reason for the existence of the moduli space. That it parameterizes canonical models of smooth projective varieties of general type. And just recall that canonical model can be defined two ways. So either as the proj of the canonical ring or the image of a pluricanonical map for divisible enough S. Okay, so there's this moduli space, and maybe like to mention that there's also a perversion in dimension one. The integer coefficient perversion was worked out by Toots and Mumford, the rational coefficient one by Hassett, and then the arbitrary dimensional one by Kolar, and also there's an alternative approach by Alexeyev and Filippazzi in Chiostro. So I like to spend now like a quarter of an hour with one construction of MG bar, which is basically the version of the construction Chenyon presented, but for MG bar. And the reason I present this construction, because after knowing this construction, it's kind of evident what the definition of stable varieties should be in higher dimensions. So, okay, so this construction, as many other constructions, start by showing that you're dealing with sorry, something went wrong. What did I do? That with you're dealing with a stack. It's just some descent statement. And then the first really important statement is this boundedness, that you want to shower all your stable curves into a Hilbert scheme of a fixed projective space, so PR, in this notation. So for this, we just use that what we learned from Harshon, that 3K of a curve is very ample. Of course, you have to extend it to stable curves. And then you just, by Riemann-Roch, you see that actually this embedding puts all your curves in the same Hilbert scheme. Now, there's a little catch that, so this picture, the bottom thing would like to be the Hilbert scheme, and the top thing would like to be the universal family over that. And so there's a little catch that when you put your stable curves into the Hilbert scheme, then you always have a choice of a basis of the tricanonical section space, and so the embedding is not unique. The different embeddings differ by an action of PGLR plus 1. Okay, and then there's another catch that in this Hilbert scheme, there's a lot of other stuff. So there's some reduced curves, or non-reduced curves, and some reduced but worse curves with worse singularity. And also there's things for which maybe the polarization from PR does not agree with the tricanonical polarization. So the good news is that you can kind of throw them away in an algebraic manner. So that means that there's a close, biggest locally closed subset over which the family is a stable family, so ample relative canonical and nodal curves. And the polarization is also correct. So this is what we call the second step, local closeness. And if you did this, then you can show relatively, I mean, it's not an insane work to see that mg bar is then just the quotient stack of this thing, this subset of the Hilbert scheme with PGLR plus 1. So for example, this implies, after you show that also the diagonal is étal, that mg bar is at least a DM stack. Good. So, and now here, and you also see that some of the coarse moduli space has to be some kind of scheme quotient of scheme version of this stack quotient. And then the question is, okay, how do I construct it? So this is where the different constructions differ. So Mumford was originally doing it with GIT. In this, in the construction that leads to the definition of stable varieties, we do this other thing, what is the same thing what Cheyan was doing. We show that the stack is proper. Then it follows that by the Kilmore theorem that the coarse moduli space exists as a proper algebraic set, and then we will find the polarization on it. Okay, good. So to show this, the most important step is to show that one parameter families, I mean, to show properness with this construction that one parameter families of stable curves have canonical singularities. So I put up here just for safety the definition of log canonical singularities of pairs because we will use them. So you just write down this Krapent equation for every birational, proper birational map, and you just require the Krapent boundary gamma to have coefficients at most 1. So that's the definition of log canonical singularities, and sometimes they defined by moving gamma to the other side, and then you're dealing with discrepancies instead of the coefficients of the Krapent boundary. So obviously the two are equivalent. Okay, and we will need also the notion of canonical, because it is essentially the same notion. Just you require the Krapent boundary to have coefficient at most 0 instead of 1. And here I didn't use pairs for canonical because I don't need it. And so maybe a little note. If you were log canonical and you had a Cartier divisor in your boundary going through your singular point, and you removed it, then obviously all the coefficients of the exceptional divisors will decrease by at least 1. So that means that in this case, from log canonical, you become canonical. Okay, this is something, please remember, we're going to use it on the next slide. And then the other thing is that the main example you want to remember of canonical singularities for this talk is that if you take the universal deformation space of a node and you just pull it back by a branch cover, which is formally locally just T to the n over C, then you get this scheme formally locally, and this is one of the first canonical singularities one learns. And then it follows that that actually the total space of one parameter families of stable curves has canonical singularities. Now, this is great, but this proof is not so great because it doesn't work in higher dimensions, doesn't work in positive or mixed characteristics. So it's very special. So let's see if there's something more somehow conceptual proof of the fact that one parameter families, and sorry, something I forgot, generically smooth one parameter families of stable curves have canonical singularities. And so the key is this theorem of chord inversion of a junction from MMP. let's take just a family of curves, a smooth family degenerating to a singular one. And let's assume that the total space is normal and the canonical of the total space is Q Cartier. So in this particular case, inversion of a junction says that if the central fiber has at worst nodal singularities, if and only if the pair of the total space with the central fiber is log canonical. And then by what I was saying on the previous slide, by removing a Cartier divisor from a log canonical pair, we get that this implies that if the central fiber is nodal, then the total space is canonical. Okay, so this is the conceptual proof. And then let's see how we use this to actually show properness of our stack. So what does properness means? That if you have a DVR and you have the generic point maps already to the stack, and then there's a unique way to extend that map to the whole DVR map into the stack. So obviously you can take this apart to saying that, well, if my DVR maps, then it's unique. So that's what I'm going to start showing here. And then if only my generic point maps, after maybe a finite base extension, I can extend it to a map of the DVR. So unicity. So unicity is somehow the key to unicity is this lemma, which is displayed on this slide. It says that if you have a family of stable curves, then and you take a resolution of singularities of the total space, then you can get back your original family of stable curves as the proj of the relative section ring of the resolution. And let's prove this quickly. So by the canonical singularity statement, which we already know for the total space, we have this condition that the canonical of the resolution is more effective than the pullback of the canonical of our total space. So then if you take m times this relation, you take the sheaf associated to it and you push forward by nu, then you get this map. And by projection formula, you can even show that the left guy is just the sheaf associated to m times the canonical of the total space. And then you see that this map is isomorphism over the isomorphism locus of your resolution. So in particular, its kernel is torsion, but all the sheaves are torsion-free because they are push forwards of torsion-free sheaves by dominant morphism. So actually, there's no kernel to this morphism, so it's an injection. And then by the fact that it's isomorphism on a big open set, so in codimension 1, this injection, and that you're dealing with a line bundle on the left side by this usual Hartog's theorem argument, you can show that actually this is an isomorphism. So this is an isomorphism, and then using this isomorphism, if you push it forward to F, so you push it forward via this morphism, this isomorphism, you just get that the relative section canonical rings of Y and X are the same. And then, of course, because Kx is relatively ample, you can get X as the proj of the relative canonical ring of X, which is, we just proved is the same as the relative canonical ring of Y. So that's it. The little lemma, the only proof you have to have in each lecture. And now let's see, from here, unicity of limits follow basically trivially. So you have two maps of your DVR into your stack, which are the same over the generic point. So that is, you have an isomorphism, you have two families of stable curves, and you have an isomorphism between them over the generic point. And then having this isomorphism over the generic point means that you can find a joint resolution. You just take the resolution of the closure of the graph of that isomorphism. And then, hooray, we use the previous slide. X can be obtained as the proj of the relative canonical ring of Y, but that's also the same as Z. So they are actually isomorphic, X and Z. So this is the proof of existence of limits. Again, we showed that if you have two families over a DVR, they are isomorphic at the generic point, then they are actually globally isomorphic. And then existence of limit is basically the same proof, just backwards. So there you start with a map to your stack from your generic point that is a stable family over your generic point. Let's assume now it's smooth because otherwise there's some gluing mass going on. And then after some finite base extension, you can assume that you're dealing with a semi-stable family. And then here comes the main important thing to understand, that because the central fiber is linearly trivial, you have that the canonical of X is linearly equivalent to canonical of X plus the central fiber. So that means that the canonical model of X is also the log canonical model of XXT. So in particular, the canonical model of X, which is central fiber, has log canonical singularities, and then by inversion of a junction, you get that the central fiber is nodal. So this, together with the relative ampleness of the canonical of the canonical model, tells you that, hooray, you have a stable family. Okay, so again, we had a stable curve just over the generic point, and we extended it to a stable family over our whole DVR. Okay, and to sum up, we have showed that we have a proper DM stack over Z, actually. So all the statements I used work over Z, and that we have a coarse moduli space, which is a proper algebraic space over Z. And the main things we used were MMP and semi-stable reduction. And in particular, we used the inversion of a junction, which is a consequence of MMP, but we also used a lot of other facts from MMP, like existence of canonical models, for example. And then having a proper coarse moduli space as an algebraic space, there's a theorem that it's a scheme as soon as you exhibit an ample line bundle on it. And this, as Chayan already mentioned today, you can do by basically taking the determinant of the mth Hodge bundle. So first you can show that the mth Hodge bundle defines a sheaf on your stack, so it's compatible with all the pullbacks, and also you can show its nav. I think for stable curves it wasn't Griffiths, Fujita, or Vivek who proved it, but they proved the other general statements before. And then Kolar has this ampleness lemma where you can look at the group action and how isomorphisms work. The key is that the fibers have only finitely many isomorphisms in the assumptions of Kolar's ampleness lemma, and then this ampleness lemma tells you that the determinant of this mth Hodge bundle is actually an ample line bundle on your stack, and hooray, you get that the coarse moduli space is a projective scheme over Z. So that's it. That's the construction of MG bar that I wanted to present you. And then the question is, okay, what can you do in higher dimensions? And the key is somehow to realize that by now at least, so it wasn't historically like that when it was developed, the theory, but by now basically all the ingredients I mentioned are available at least over the complex numbers in any dimensions. So this whole construction has to give something. You just have to understand what it gives. And to what it gives, you have to understand what functor you should write down for which this construction gives you the moduli space. And So, okay, here, okay, I said in words what is written here, that everything is known in higher dimensions over C. And then to figure out what functor you should write down, inversion of a junction is the key, right? I hope I persuaded you during this little MG bar construction. And so you have to figure out if you have total space Pascal's fiber being log canonical, what does that correspond for the closed fiber? And luckily, this is not something which is an insane task to do at the current level of our knowledge. Of course, it wouldn't have been that easy 30 or 40 years ago. But by now, we know that it's semi-log canonical is precisely the equivalent of XXT being log canonical. This is a notion that it's kind of, so when you have semi-log canonical singularities, you will have nodes in codimension 1, and you will have log canonical type singularities in higher codimension. So the precise definition is as follows. First, you require that you are S2, your space is S2. So this is this Hartog's extension theorem for local functions. So whenever you have an open set, such that the complement has codimension at least 2, then having a local function on that open set or just the local function is the same. So that's what S2 is. But of course, we all learned it from Hartshorne, so we all know it. And you also ask that in codimension 1, you have regular or nodal points. So this together gives the notion called demi-normal. So that's how you start. You replace normal with that for your space. Then you ask for your canonical to be Q-Cartier. And then, by the way, maybe a short story. It's not semi-normal because that was already taken. So, okay, and then you finally ask that the normalization with the conductor divisor is log canonical. And that's it. That's the precise definition of being semi-log canonical. So this will be the singularity. So whatever construction I presented will work with these kind of singularities. Hence, you define stable varieties to be gadgets that have these singularities, semi-log canonical plus ample canonical, because of course the construction works with ample canonical. And then you try to write down the functor. You require the obvious flat. You require that the numerical invariance, the dimension, and the volume is correct. And then there's one more catch, that the whole construction was based on relative canonical rings. And you should require that these are functorial. And so that's what this last condition tells you, that the concerned sheaves in relative canonical rings are flat and compatible with base change. It's famously known as Collar's condition, because somehow this was really not evident, this condition, and János figured it out that this has to be there. Okay, so that's the functor for when you have no boundary. What's the functor when you have boundary? It's a bit difficult to write it out, especially in the arbitrary coefficient case, especially if your coefficients can be real. So coefficients, I mean these CI. So let me give you sort of more like a recipe, how to come up with a functor. So, of course, you're taking families of some pairs, and you write the boundary as the sum of CI that you think about weights that maybe you want to move around later on. So these are either rational or real numbers, and the DI, which are just effective divisors. And you copy kind of all the conditions that was on the previous page for the boundary-free case to this pair case. And then you wonder whether it works. And then you figure out it works pretty well for reduced bases, but for non-reduced bases, it doesn't work. And so Collar's solution for non-reduced basis is to add this condition that the di are k-flat, which is a very intricate notion. Let me not talk about it. But so János wrote a great book recently appeared where all the details are worked out. And then, I mean, of course, there's challenges with this notion of k-flat. For example, we don't know if there's a good description of infinitesimal deformation spaces. And I talked here at the conference to other people, and it turned out there are also other things that we don't know. But at least it seems to be giving a clean functor and a clean moduli space. Another alternative approach is by Alexeyev and also worked out in details by Filipazzi Inchiostro. So here you kind of, I mean, actually all the problems here come from something that when you learn algebraic birational geometry, think that just a technicality, that there's divisors that are not Q Cartier or not R Cartier. And actually, as you get older, you realize that that's actually a really, really important stuff. And somehow a lot of things do or die, live or die based on whether things are Q Cartier or not. And so somehow the approach here is that you perturb a little bit. You act like you make it Q Cartier. You pass to a little higher model. And you don't expect divisors, so it's by a small map where things become Q Cartier. And additionally, you can make this little perturbed divisor ample. And then it was worked out by these authors that you also get a moduli space this way, stack and coarse moduli space too. It's easier actually to write down the construction, the proof for the second functor, but it has little disadvantages that it's not completely canonical. You're choosing some kind of direction in the space of weights. So yeah, these are the two options. Again, the reduced structure is the same on them, but they give two different infinitesimal structures on the moduli space. So these are the functors. And then you might wonder, okay, how much it is known that these functors actually give you the moduli space? And the answer is as much as the ingredients are known. So I persuaded you, hopefully, on the previous slides and the MG bar construction that the ingredients are these three and these three. So let's talk about where they hold. So the general phenomenon that everything works really fine over the complex numbers in any dimension. For example, for boundedness, this was shown by the famous paper of Haken, McKern, and Shu. It also holds a lot of times in prime characteristics or over the integers, or so in mixed characteristic for surfaces. And then in mixed and prime characteristic for higher than dimension 2, not much is known. You see the same thing all around for all ingredients. Locally closeness is a bit different because that's kind of known. But for example, MMP has the same thing, like you have the BCHM and the follow-up results in arbitrary dimensions over the complex numbers. And then Haken, Shubirkar, and others showed what one needs here in dimension 3, which you need for the surface for surface moduli space. You need dimension 3 MMP, characteristic 3, and then the 7-author paper about which you already heard a 3 lecture series this week in mixed characteristic. And then semi-positivity is similar. By Fujino, it's known, as Chen-Yang already mentioned in the morning, it's known over the complex numbers in any dimensions, and I proved in mixed characteristic for surface pairs. And then then maybe yeah, so for ampleness lemma, the Collard's original ampleness lemma was working for what works in all situations if you don't have pairs. And then in the pair situation, Kovács and me, we had one solution, and Philippe Zinchiostro another one. And then the bad news is semi-stable reduction. It's known completely in characteristic 0. But in mixed and positive characteristic, the only result, or there's maybe similar results also by others, but all of them are the same flavor. You have to have some kind of relation between the volume of your polarization and the characteristic. So somehow the characteristic cannot be small with respect to the degree of the polarization. Okay, and you put all this together, you have everything what you want. So the existence of the stack and of the coarse moduli space in any dimension in characteristic 0. And in mixed characteristic, because you don't have semi-stable reduction, the best you can do is a stack which is maybe not proper. And it's also not DM because it might have the automorphism groups might be non-reduced. So it's an Artin stack with finite diagonal. And then, but at least by the Kilmore theorem, we know that a coarse moduli space exists at least as an algebraic space. And then you can turn this into a projective coarse moduli space only if you can somehow, you put yourself in a situation where you can apply this kind of volume characteristic related semi-stable reduction. So for example, we wrote this out in one of the 7 author articles that if you exclude some characteristics, but the amount of characteristic that you exclude depends on the volume, then at least the closure of the locus of smooth surfaces is has a projective coarse moduli space and is proper as a stack. So okay, so these are the positive results, and then because mixed and positive characteristics should also deliver some excitement. There's some negative results also in positive and mixed characteristics. So János proved not so long ago that starting with 3 folds, the moduli space is not proper in mixed characteristic. Maybe one little remark that his examples are not Cohen-Macaulay, and over C anyways, the moduli space is a disjoint union of the Cohen-Macaulay and the non-Cohen-Macaulay part. So one could hope that maybe one can remedy János's counterexamples by showing that the Cohen-Macaulay part at least exists in mixed or positive characteristic. But then my former student, Kantan Posva, showed that even this doesn't work. But at least the characteristic is bounded by the dimension. So then let me conjecture that the Cohen-Macaulay part is proper at least when you exclude some finitely many characteristics where the finitely many depends on the dimension. So let's see in 35 maybe this will be proven. Okay, so that's about what we know about this the construction of these moduli spaces. And then what else do we know? So first, let me talk about the general facts or general statements that's known for all or a general component with certain properties. So first, the bad news. I'm Hungarian. I have to start with the bad news. So Ravi Vakil showed that any singularity can show up on these moduli spaces already in dimension 2, and then also in all higher dimensions, this is the case. So somehow you have to be careful when you work with them. but still, there is a chamber decomposition. So so this was a theorem that I proved with Escher, Bailey, and Inchiostro. So let me kind of explain the framework. So it's the chamber decomposition. It is with respect to moving around the weights. So you fix some polytope P on the slide where you will move around your weights. And I present a simple case, which is easy to state, and the strongest statements are true. But there's much more generality in which you have this kind of statement. So let's assume for simplicity that we have a for each choice of weights, so for each choice of weights, we have a relatively normal crossing family. And for each choice of weights, for this family, the relative log canonical is relatively ample. So what do we try to do? We move around the weights and we look at the compactification of the closure of the image of the moduli map of this family. And as you move around the weight, this closure will change. Of course, the core part, which is given by the family itself, will be the same, but the closure itself not. So you will get birational stacks or varieties. And the question, what can you say? How do they change? Maybe if you want to think about an explicit example, then probably the best is to think about, for the first, is P2 with a sextic curve, and the coefficient is at least 1/2. So the theorem says that luckily there's a chamber decomposition, which is pictured in a Dadaistic manner up there. So when you move in the chambers, so let's say you're in one chamber, then your moduli space in the interior, then the moduli spaces will be isomorphic. And then when you get to the boundaries, so you get to some boundary, then you have a flip-like behavior, although from the smaller weight, going from smaller weight to the boundary, actually that morphism becomes isomorphism if you normalize the moduli space. So it's more like really just a contraction, at least after normalization, on the boundaries of the chamber. So you at least have this kind of chamber decomposition. And then one can ask if there are, how this chamber decomposition actually looks like. Unfortunately, this is relatively new, so there's not so many explicit results at this point. Let me just mention two sets of them. One is for these del Pezzo surfaces polarized by the -1 curves in them. And the other one is not really a chamber decomposition, is just understanding what the smallest chamber. So first showing that there's a smallest chamber. So when you converge to the point where you don't have stable varieties anymore, whether you have infinitely many smaller and smaller chambers or just one big chamber. So they showed that there's one big chamber. And what I forgot to put here, because that's not so explicit, but Chenyan and Janos then showed that this happens actually in general, not just in these explicit cases. Okay, so these are the examples of wall and chamber decomposition. And then what other questions can you ask in general about the geometry of this moduli space, which is still you can work on even if the moduli space is not smooth. For example, sheaves. What sheaves do you have? So Chenyan already mentioned some of this story, but I'm just going to re-say it. So first, Fujino's and Kollar's original work shows that this determinant of the ample, the Hodge bundle is an ample line bundle for divisible enough M. And then with Kovács, we did this also in the log case. So you know that there's an ample line bundle, but you might ask which one. Can you write down one? Because it's divisible enough M, it's hard to know what divisible enough means from the proofs. And so one thing you can look at is that if you take this determinant and you rescale it, luckily I think my constants are the same as on Chenyan slides, then you converge to something. So that something is called the Chow-Mumford divisor, and you can define it also a different way, which is written down here, at least when the base is normal and projective. So all those test families for which the base is normal and projective, you can define it as so n the relative dimension of the family. You take n plus 1 self-intersection of the relative canonical divisors. So it's self-intersection, not powering, instead of, because all the other places they were powering. And then you push it forward as a cycle, not as a sheaf. All other places on the slides were sheaf push forward. So be careful. These are, and anyways, so this gives you a cycle on all normal projective bases. And one can show that it extends even for infinitesimal bases to a Q line bundle. So meaning some power extends to a line bundle. Okay, so you have this Q line bundle, its limit of ample, so it's NAF, but is it ample, right? So the good news is, which now you heard already from Chenyan, so not a surprise, that we showed that it's actually ample. But then, okay, so there's one explicit ample line bundle you can write down on every family. There's, on the other hand, you might wonder still whether if you just go back here and you take determinant of the M Hodge bundle, whether that thing maybe works for any M, and then you have something that you actually can write down. You have more things that you actually can write down. And so for this, first you have to show that this formula defines at all a sheaf on the moduli spaces. Is really tricky because the relative canonical here is not a line bundle. It's just a Q-Cartier divisor. So you're pushing forward just Z divisors or the sheaves associated. So S2 sheaves. But everything somehow is working in a way, some serious theorems you have to throw in, but eventually you, so Kollar and Fujino, so Kollar showed that, yeah, anyways, so this works. And then, I mean, Kollar basically showed some local Kawamata-Fivek vanishing, and Fujino showed the global Kawamata-Fivek vanishing that you need for this. And then, okay, so now you actually have for every M here a vector bundle on your moduli space. So you can ask whether it's NAF. And to my biggest surprise, we proved that it is. When we started this project, I was sure that this is just no way it's true. So this is a joint work with Codogni and Tassin. And then we could even show that if you take determinant and at least you are in the KLT locus, then you get something ample, assuming that you're not zero. And then, for example, a random application of this, that you get a lower bound on the volume of the CM line bundle on those components which contain a KLT point. So this is, yeah. I mean, in the analytic approach, they look a lot about volumes of these metrics. So I think this is maybe a natural question statement from that point of view. Okay, so that's what I can say about what's known about sheaves and divisors on these moduli spaces. Then maybe the last general theorem I want to mention is something I already mentioned. Kollar and Kovács showed that the Cohen-Macaulay and the non-Cohen-Macaulay components are disjoint, like it's a disjoint union of them, the moduli space. And so the Cohen-Macaulay part is the more interesting, at least if you don't have boundary. If you have boundary, then maybe it's an overstatement. But if you don't have boundary, then then all the canonical models are KLT, are Cohen-Macaulay. So so they lie in this connected component. And in this work, they also showed that if you take HI of the structure sheaf, that is compatible with base change. I mean, the adequate like push forward sheaves for families. And so you get also a sheaf on the moduli space. So I was lying. There's one more sheaf I can show you. Okay. And then come the bit more restricted theorems in generality, but then of course there's much more detail to them. So there's first this recently, so this question has been out there. It has been a famous question of Donaldson apparently, which that whether there's a perfect obstruction theory on these moduli spaces, so you can count stuff. So the relatively recent result of Jiang, you can do it at least on the KRT locus in surface cases. And then there's ongoing work and follow-up articles where they count surfaces or maps from surfaces. And then you can also do a lot of explicit compactifications. I'm sure I forgot some of them, so I'm terribly sorry. I probably also forgot some authors. Again, terribly sorry. Yeah, so for example, the abelian variety compactification is a widely used one. So these then find a lot of applications which are not necessarily about stable varieties. And then I'm not sure what to add. For example, the surface of general type story also has they go for a lot of applications, whether things in different components are diffeomorphic or such questions. And so in this direction, applications, let me conclude with applications in which statements in which there's just no mention of stable varieties, but the proof use the moduli space of stable varieties. So let me first start with this famous theorem of Lee and Park from almost 20 years ago, I think, that there are smooth projective simply connected surfaces of general type with zero genus and volume 2. So this was not known at that point. Now much more is known. So for all possible volumes, it's known by now. So it was a big surprise when it was shown. And so they were taking some stable surfaces and they showed that they can be smoothed out in a way that they could control the numerical invariance and the topology. Then with Kovac, I showed subadditivity of Kodaira dimension from open varieties. So this is, again, doesn't have using moduli space of stable varieties. So again, a statement that that doesn't have anything about stable varieties in it, but the proof uses. And then finally, in this recent work with Kononyi and Tassin, by understanding sheaves on moduli spaces, we are able to bound from below the relative volume of fibrations from n+1 dimensional variety to a curve with KLT general fiber and ample relative canonical, and we also have to assume it's not isotrivial, otherwise the volume is 0. So this is also an application where, of course, I have to admit that this particular application looks much closer to stable varieties, but still, there's no mention of stable varieties in the actual statement. So thank you. I would like to conclude with this picture of a Whitney umbrella, which is very useful if two of you are walking in the rain. Also, it happens to be a singularity called pinch point in algebraic geometry, which is super important for for the moduli space of stable varieties. So thank you very much.